let's talk a little bit about how you'll approach the design of percolation. So you can think of the percolation data type as a sort of strange accountant. You give it commands. You say, hey, accountant, open up these squares, and that class is going to use whatever instance variable it has to answer your questions later. So for example, if I say open a bunch of sites and then I ask is open, I expect my weird accountant to be able to tell me which ones are open. And so is open will be relatively straightforward, but it gets more interesting when we start asking the accountant, hey, I told you to open all these sites, but is this one full? Okay. So I'll give away a little bit of design here. One way to do open is open. You can imagine in your percolation class having a two-dimensional array of booleans, and when you say open, you just flip any square that's open to true. And then when you do is open, you just return what's in the box. Okay? So that's sort of the obvious way, to me, to implement open and is open. But for is full, it's a little trickier. For is full, you might need to, for example, scan through each line of the universe from top to bottom, wait until you get to the site you want, keeping track of some kind of, I don't know, complicated information, some kind of fancy algorithm, so that you can use your two-dimensional array of true-falses to get the answer. And similarly for percolates. Now, we don't want you to do some kind of fancy simulation, though. In fact, that was kind of a cool move. In fact, what we want to do is we would like to take advantage of what we did in the recent lecture where we discussed the disjoint sets problem. We're going to leverage the power of the disjoint sets problem, or the disjoint sets data type, in order to solve this problem efficiently. So in particular, you guys are going to use a class that's in the Princeton Standard Libraries called Weighted Quick Union UF in order to solve this problem. And I'll talk a little bit more about what that might look like. But basically, the idea is you get to make the choices about which instance variables you'd like, but it's very important that you obey the rules, which is that all methods should take constant time plus a constant number of calls to these methods here. Because this is a homework and not a project, I'm going to give some spoilers. And you should feel free to take advantage of these spoilers or not, but if you want a little more of a challenge, maybe skip the rest of the video, but I'll give some tips about how you might use the data structures provided in the Princeton Standard Library to make the percolation data type work. So I'm assuming if you're watching this video that you are familiar with the disjoint sets ideas from the previous lecture, where we had a data type, here it's linked, a data type which supports connect and is connected. And so in this assignment, we're going to use the Weighted Quick Union UF class, which is provided in the Princeton Standard Library. And so this data type supports three operations: union, which is the equivalent of connect in our lecture data type; connected, which is the equivalent of is connected; and it also supports an additional operation, find, which tells you which set a given item belongs to. You don't have to use this, but you might maybe find it helpful if you want to think about things a different way than what I'll present in this video. Okay, so that's the data type we're going to use, and that's what we're going to have as our accountant, so to speak, for our percolation. As an example, let's consider a 5x5 world. It's not a very big one, but we're going to start digging inside of this world and seeing what our data structure is supposed to do. So initially, if I call is open, is full, or percolates on any of these squares, it should say false, right? Nothing is open, nothing's full, and the system does not percolate. Now when we dig out a square, say 3, 4, using the open command for our percolation data type, we need to record in our data structure somehow that this space is open. And at that point, as we said earlier, you could just make a two-dimensional array and that'd be fine. But where things get more interesting is when we open a space next to that. Why is this more interesting? Well, we have to keep in mind that we're using percolation as a funny sort of accountant, and we need to record somewhere that these two spaces are connected, because we need things to be really fast later. Okay? I guess maybe the intuition more is just that if water flows into one of these squares, we want it to flow into all of them really quickly. We don't want to do any kind of simulations. We should just record that these two spaces are connected so that we know this, right? Because remember, the point of the disjoint sets data type is to track connectedness of things, and surely these now are connected. So you might imagine trying to call the union command. Remember, union's kind of like, it is the same thing as connect from lecture. We might try and union, 3, 4, 2, 4. We try and make a call saying these are the two locations I need. However, this will not work. If you look at the API of the Weighted Quick Union UF data type, it does not take whatever these things are. It only takes integers, just like we did in class. Let me make sure that's very clear here. Union, int p, int q. Every item has to be represented by an integer, not by a pair of numbers that indicates a space on a grid. So you need to translate somehow. So here comes huge spoiler number 1, which is it makes a lot of sense to assign each square a number. Okay? And what do I mean by that? What I mean is that anytime you try to access square 2, 4, you can also treat that as square 14. So that if we're trying to use a disjoint sets object to track the connectedness of things, then we need to have that special now one-dimensional coordinate. Okay? And so to make this easy, my biggest recommendation, that's a little thing, but it's so important. One of the things that you might have suffered with in programming in the past, say Project 2, is knowing how to modularize things. And this is a great example of how a little helper method can make your code so much easier to read. So I would highly recommend having something like xy to 1d, where you give it a row and a column, and it gives you back a number. Okay? Or you could also call this rc to 1d, whatever name floats your boat. But basically, if I give it 2 and 4, it should give me back 14. Okay? And that will make your life much easier. All right, so that's what opening 2 adjacent sites might look like. Now let's say we open 2, 2. Quiz for you. Do I need to call union? Think about it. Okay, the answer is no. This space is not connected to anything. So if we're using a union find object to track connectedness, we do not need to say it's connected to anything. I mean, right now 12 and 7 are not connected, right? This is still full. Now if later we come along and we open this square, then we need to do some unioning. In particular, we need to union space here. We need to union 2, 3 with 2, 2 and 2, 4. And if we're using this function I recommended on the previous slide, that means we're going to union 12 and 13 and 13 and 14. Okay. Next up comes opening 0, 2. And in this case, there is no unioning, but you'll notice I'm using the color to represent full, but we're not doing anything special, right? The only thing we did was mark this as open, but now, when we call isFull, well, presumably this should return true, but we'll talk about how isFull might be implemented later. Okay. And then finally we do a last open I'm going to do in this example, which is to open 1, 2, in which case I need to union 2 and 7 and 7 and 12, and I'll now have noted that all of these are connected. Okay, so that's the idea about how you can track the state of the system. If you're making these union calls and you're storing everything in a 2-dimensional array of true falses, you have all the information you need in order to implement the other operations. For example, isFull. So how do I implement isFull 2, 2? I need to somehow figure out if this space is actually full. Well, there's a number of different possibilities. And one of them I alluded to earlier is scanning through here and doing some kind of like, okay, well, if this one's full and this one's full, like I'll trace down a path, yada, yada. But you don't actually want to do that. Because of the fact that we're using this disjoint sets object, the disjoint sets object is going to, 1, save us lots of work, and 2, it is going to be faster. So think about how I can use the connected operation here, right? So what connected calls do I need to make to test and see if 2, 2 is full? And this one I really want you to think about, and I will spoil it in a moment. So the most obvious brute force approach to figuring out if this site is full is to check, is it connected to site 0, site 1, site 2, site 3, or site 4, right? So we just manually check all of these connected, and if it's connected to any of those, then it's full. Now the problem with this is it's too slow. Recall in the spec we said you must use only a constant number of operations of each of the given types to support in each of the percolation operations. So in other words, to implement isFull, you cannot call this more than a constant number of times. And so for an n by n grid, we'll note here we're doing it n times, so it's actually a linear number of calls, which is too slow. So we want to make our simulation faster. Now one thing I might recommend is you might actually at this point just call it a day on watching the video, go try and implement this, and just get it working the easier to understand but slow way. And then once the visualizer is behaving properly, then come back and try and speed things up. And so in the next video, what I'm going to do is give some spoilers about how you can make this faster. But again, you might consider actually trying to get all this working and then come back and watch that video and speed things up.